It's a pleasure to introduce Daniel Beltita from the Instituto de Matemáticas de la Academia Rumana, that is going to speak about intrinsic symmetry of von Neumann algebras. Thank you.
Thank you for this introduction, and a special thank you to everybody for inviting me to give again a talk in the seminar. As always, I'm very happy to meet everybody, and at least virtually. I will speak about a few results that are obtained a few years ago together with a friend that who unfortunately passed away a few years ago, namely Anatol Odzijewicz. And I'm revisiting, these days I'm revisiting these results in order to try to make some further progress. So I thought it could be a good occasion to present them here, especially as they are, as you will see, they are related to the work of quite a few people from the audience, and I will mention that when the time will come. So the topic is about the symmetry that is intrinsic to von Neumann algebras, in the sense that I'm going to explain that whenever we have every von Neumann algebra carries along a considerable amount of symmetry that may not be obvious at the beginning, but I hope to convince you in the end that it is there. The most basic idea of symmetry that appears in the theory is provided by the basic theorem of John von Neumann on the bicommutant theorem that says that together with every von Neumann algebra, we should study the commutant, and we basically cannot distinguish them from each other in the sense that the algebra is the commutant of its commutant, so we can start with the commutant and we have exactly the same picture. Important is the pair of the algebra and its commutant. But I'm going to show that it's more there is more symmetry in the theory than just that basic symmetry. The plan of the presentation will be to firstly recall a few basic facts on operator algebras that are certainly well known to you, but I'm going to use some notation that is slightly unusual, and so I have to introduce it. And after that, I will briefly recall again, for the sake of making precise the notation, a few ideas on groupoids, since the way we formalize symmetry uses the language of groupoids. The notion is pretty well known by now, so I will not dwell too much on that. And in the end, the main point will be that to apply this language of groupoids in order to describe the symmetry that is encoded in the standard forms, namely the forms that appear in the so-called Tomitata-Kesaki modular theory of von Neumann algebras. And I will also discuss some examples. The notation that I said was a bit unusual is this one. L by L infinity of H, I will denote the set of bounded linear operators in order to suggest that this is a kind of non-commutative analog of the space from measure theory. We will need the positive cone in this in the algebra of all bounded operators, and also the trace, the canonical operator trace that may take infinite values, and it is independent on the orthonormal basis that we use for this definition in this way. The trace, with the trace at hand, we can define the ideal of trace class operators, and this is denoted by L1 because it is the analog of the non-commutative analog of the space of absolutely integrable functions. And we have the trace allows us to define the duality, the bilinear map defined in this way by the trace, and it gives the fact that L1, the dual of L1 is L infinity, which is well known. And using this duality, this isomorphism, we can endow L infinity. Besides the norm topology, we can also endow it with the weaker topology that, which is a weak topology defined by this duality, and I will denote it by W star. And as we know very well, this is actually the natural topology of von Neumann algebras. So we will need it. And now for operator algebras, for any subset, any set of operators, we denote its commutant by A prime. And then we can iterate to take the second commutant, which in particular contains the initial set of operators. And the bicommutant theorem of von Neumann says that star subalgebra of L infinity of H is unital and weakly closed if and only if it is equal to its own bicommutant. So a purely topological property is expressed by a purely algebraic property, and it is part of the magic of von Neumann algebras that this theorem holds true. And here we have what I mentioned before, the basic symmetry between M and M prime, that since M prime, of course, can be obtained from M, but also M can be obtained from M prime as the commutant of M prime. Now, by W star algebra, we will mean any star. All the time when I will say, I will not specify by algebra, I mean associative algebra. So it's an associative algebra with an involution that is algebraically isomorphic to a von Neumann algebra in the above sense. In some sense, we could call them abstract von Neumann algebras, or the von Neumann algebras are called the concrete W star algebras. And just as in the case of L infinity of H, which is the first example of von Neumann algebra, we have a predual. So if we have a W star algebra in this way, then if we have a von Neumann algebra or a W star algebra, we can consider the set of weakly continuous linear functionals. If they are weakly continuous, in particular, they are bounded. They are continuous with respect to the norm topology. So this is the complex Banach space, and its dual via the natural duality pairing is its dual is our von Neumann algebra. So the situation mirrors what happens for L infinity of H. But our main concern will not be with this complex Banach space, will actually be with a real subspace defined by the Hermitian linear functionals. This superscript H stands for Hermitian. So the functionals satisfying this property. As we see from this property, this is only a real Banach space, and we can naturally compute its dual space. It turns out to be this the space of skew adjoint operators. Of course, it is also isomorphic as a real Banach space with the space of self-adjoint operators, but we like this more because it has the additional property of being a Lie algebra, so it is closed under the commutator of two elements. And we have this duality pairing. So, of course, with the suitable normalization, that is why we use here the subscript R, because we need to multiply by I. It is not the same as the above duality. It's not the restriction. We need to normalize a bit. All these are well-known facts from von Neumann algebras. Now there comes the first piece of symmetry that goes beyond this basic symmetry between M and M prime. And this is encoded in the space of smooth functions on the predual. I say on the predual for the sake of brevity, but actually we work on the space of Hermitian, on the Hermitian part of the predual. So for every smooth function on this real Banach space with a function with real values, we have its differential in the sense of Fecha differential calculus. And so the differential at one point is a linear functional on this space. But the dual of this space is this Banach algebra. So via this identification, we can say that we can think of the differential of the function as a map from the Hermitian part of the predual into this Lie algebra. As this map takes values in a Lie algebra, we can perform the following construction, the so-called Lie Poisson bracket. Namely, if we take two smooth functions like above and an element in the predual, then we can we compute the differentials of the functions at that point. They will be elements of this Lie algebra, so we can take the commutator. It will belong to the same algebra, and then we can apply via the duality pairing to the point where we did the computation. Please notice that this expression in the right-hand side is by no means linear, because this df is of course does not depend linearly on the point where we take the derivative. So by this formula, for any two smooth functions, we obtain another function denoted by curly brackets like here. And this simple construction has the following properties. It defines a bilinear map on the space of smooth functions with the values in itself. And it has the following properties. It is skew symmetric, satisfies this Jacobi identity. So in particular, it is a Lie algebra bracket on the space of functions. And moreover, it is compatible with the pointwise multiplication of functions, because this space of smooth functions is of course an associative algebra. So the Lie bracket is satisfies this property that basically if we fix a variable, it is a derivation with respect to the other variable. If this were a finite dimensional space, then we knew that every derivation is a vector field, but it is not. This is not a finite dimensional space in general, so we only know that this is a derivation in every variable. A bilinear map on a commutative algebra that satisfies these three axioms is called the Poisson structure on that algebra. And for instance, if we have a smooth manifold with the Poisson bracket on the space of functions on that manifold, we call that manifold as a Poisson manifold. And for this reason, this is called, we can say that the Hermitian part of the predual has a structure of Poisson manifold, but of course Banach manifold. And the name of Lie comes, it's an interesting story, but I don't have the time to say that. Essentially, this formula goes back to the work of Sophus Lie, namely in the second volume of his treatise on transformation groups. He basically introduced the Poisson structure and by such a formula. Of course, at that time, he didn't defined abstractly the notion of Lie algebra, but he defined this on the set of vector fields. For him, this was what he called the differential infinitesimal group, and we call it today Lie algebra. So in any case, we have this nice structure on the predual of a von Neumann algebra. And since we have in particular a Lie algebra, it must encode an amount of infinitesimal symmetry. So this is additional symmetry of a von Neumann algebra that did not appear previously. As an example, to see what kind of information we can recover from this symmetry, Let us construct these simple functions, linear functions. So for every element, skew adjoint element in the Lie algebra, in the von Neumann algebra, we can form the corresponding linear function on the predual. As this is a linear function, its derivative is of course constant, and its value at every point is exactly the element that we started from. And then it is natural that if we take the Poisson bracket of two such functions, we obtain the function corresponding to the commutator of the two elements. So the mapping from x to f sub x actually gives us an embedding of the Banach algebra of skew adjoint elements into this Poisson algebra of functions. So this shows in particular that essentially the whole von Neumann algebra, of course only the skew adjoint part, but we can take we can extend by linearity to the whole algebra. As a Lie algebra, the whole von Neumann algebra is contained in this space of smooth functions on the predual. This already says that we basically have here the whole algebra and even more. Of course, it is not so easy to use this information for the reason that this is a Banach space that has a pretty pathological structure in the sense that it is pretty far from a Hilbert space. In particular, it does not admit bump functions. In fact, one can prove that if the algebra, von Neumann algebra is infinite dimensional, then this space does not admit smooth functions with bounded support. So all functions that appear here are, if not like this linear, at least they should be a kind of polynomials in such functions. But in any way, we cannot find here any function except the zero function, any other function with bounded support. So it is rather, maybe it should be better thought of as a kind of algebraic object, this space of smooth functions. This is something that certainly would be interesting to understand in the future, the structure of functions here. So this is the first piece of symmetry, but we are going to find more. More exactly, we have to, this is an infinite dimensional algebra, but we will renounce a bit of this infinite dimensionality, but we'll get some more symmetry by using the groupoids. Since whenever we have a Lie algebra, it's natural to think about the corresponding Lie group, if it is the Lie algebra of some group. Sometimes it makes no sense, but this idea is fruitful nevertheless. In this connection, what I am talking about here, it leads us to the idea of a groupoid. So the attempt to integrate somehow this Lie algebra to some kind of group-like object leads us to groupoids. And I will now recall briefly what the groupoids are in order to fix the notation. The basic example is a disjoint union of two groups. This is a funny object if we regard it as an algebraic structure, because we cannot multiply one element of G with an element of H, since there may be absolutely no relation between the two groups. However, we can think that we have a partially defined multiplication on this set. Namely, we can define we can multiply two elements only if they belong to the same group. And the groups are obviously the fibers of this canonical projection, the projection that has as its base the set of the two unit elements of the group, of the groups. And this is actually a kind of very simplified picture of a groupoid. Namely, in general, a groupoid is a set endowed with a partial multiplication that is exactly as a group, except that we have several unit elements, not only one. So we have a set of unit elements. Each of these unit elements, of course, should be embedded into the big set, because also the unit elements belong to the groups. We have some maps, source and target, that tell us where the elements start and where they end. And because the multiplication, I said it was a partial, we have to say what is the set of composable pairs. And the composable pairs are in some sense like the functions, so they can be composed if and only if the source of one of them is the target of the other. And we think of the elements in the groupoid as arrows going from right to left. So I repeat, from right to left, not like here, the opposite. So the source of gamma 1 is the target of gamma 2. And we also we have the multiplication map, which is a kind of similar to the composition of functions, the inversion, because it is exactly as a group. And we have associativity unit element inverse whenever they make sense. That is, when we write, for instance, associativity, we have to make sure that all the elements appearing there belong to the set of composable pairs. I will denote the groupoid by like this, but the two parallel arrows stand for the target and source. But I will never denote the T and S because we use the same notation for all groupoids. Other people denote the source and target by alpha and beta, or other people denote them by other letters, but I will prefer source and target. So that is why I insisted to discuss in detail this. And the shortest definition and the most implicit is that a groupoid is a small category whose morphisms are invertible. Small category means that the collection of objects of the category form a set. That is why we say it is a small. So for instance, all the sets with the morphism given by bijections, this is not a groupoid in this sense. We can draw the picture like this. So the arrows are, as I said, from right to left, and we can compose them if they match, the source and target match. We could have arrows that go from one point to the same point. This is exactly the picture of a group, when we have only one element, one unit element, and all the arrows, any two arrows can be composed. But if the arrows go from one point to another point, it may happen that not any two arrows can be composed, and the inverse goes in the opposite direction. We will talk about Banachly groupoids also. But now, as soon as we have at hand the algebraic structure, everything is just as in the case of groups. So a Banachly groupoid is the groupoid for which everything that appears are smooth manifolds. They could be finite dimensional manifolds for Lie groupoids or Banach manifolds, as you know very well, for Banachly groupoids, and the structural map should be smooth. What I wish to emphasize is that the source and target should be not only smooth path submersions. Why? Because we need to make sure that the domain of the multiplication is a smooth manifold. We could require that it is a smooth manifold and give up the idea of submersions, but this is slightly this can create some problems when we perform operations with the groupoids. We prefer to know from the beginning that from another source that this is smooth, not not by hypothesis. More specifically, how we prove that this is a manifold? For it is a pre-image of the diagonal map. So this means the set of pairs for which source of the first is target of the second. That is the pre-image of the diagonal. And the diagonal is a submanifold in any way we wish. And the pre-image of a submanifold through a submersion or even through a map that is transversal to the diagonal will always be a submanifold in G cross G. So we do have a smooth structure on this set of composable pairs. But we don't need to worry too much about that technical aspect. And let me go on to discuss, to present very briefly two examples. The first, the basic example of the unitary group that several people from the audience studied quite a lot. It is a groupoid who's with only one unit element because it is a group. In this way, every group is a groupoid and every Banachly group is a Banachly groupoid. The second example replaces the unitary operators by partial isometries. And this is really a groupoid which is not a group. As the partial isometries, for instance, on a Hilbert space, can be regarded as unitary operators between different closed subspaces. And so the initial and the initial space of the partial isometry will be the source, and the final space will be the target. So it's exactly the typical groupoid that is not a group. The objects, in the case of a general von Neumann algebra, the objects are the set of projections, orthogonal projections, which are in particular partial isometries, of course. The arrows are the partial isometries defined by the elements in the algebra with the property that the V star V and also V star are orthogonal projections, or just this condition is enough, but it's better to keep in mind that also the final space is the projection. The object inclusion map, because as I said, every projection is a partial isometry. The source target map are the initial and the final projections. The multiplication is the usual operator multiplication, except that we restrict it to the pairs of partial isometries whose source and target match. And this ensures that the product is again a partial isometry, as it could happen that if we don't have this condition, it could happen that a product of partial isometries is not a partial isometry. And the inversion map is given by the adjoint. This is the typical Banach-Lie groupoid, so these sets have structure of Banach manifold, and the corresponding maps are submersions and so on. Before going further, since now we have all the definitions, I would like to briefly comment on why we want to build group-like structures out of operator algebras. The basic idea is that according to the Felix Klein's Erlangen program, the geometry is the study of invariance of a transformation group. And we could easily replace the group by groupoid because the groups are not enough for several purposes. So from this point of view, every group-like structure constructed out of an operator algebra provides some geometric perspective on that operator algebra. And this is actually something that also you know very well, since quite a few people studied these structures of this type, maybe starting from Cadison, so far as I know, studied unitary groups, then Horacio Porta and Lazaro Recht, Grassmann manifolds in sister algebras. But although they are not group-like structures, they are the base of a certain principal bundle, and the principal bundles are the primary source for a class of groupoids called the transitive groupoids, namely for every principal bundle, the set of equivariant isomorphisms between the fibers of the principal bundle form a groupoid, the so-called Ehresmann groupoid, and play a key role everywhere. And even this first example allows me to make the point that many geometric structures associated to operator algebras are turn out to be actually pieces of a bigger picture that is actually a groupoid that actually collects everything and puts everything in order. Also, of course, Odzijewicz and Raciu studied what I said before, the Poisson bracket on the pre-dual Poisson bracket that was actually discovered by Pavel Bona for L infinity of H a few years before. Then Esteban Andruchov, Gustavo Coraci, and Mostafa Bekta, they studied the maps that were actually in the previous, I mean the source and target maps in the groupoid of partial isometries, as I call it now, but they proved before that they were submersions, so the fibers were submanifolds. So again, some basic elements of groupoids appeared before we start talking about groupoids. And eventually, Anatol Odzijewicz and Aneta Sujewska studied more about groupoids, the groupoids that appeared on the previous slide. And eventually motivated by these things and others with Fernand Pelletier and other Polish colleagues, we started to build the general theory of binary groupoids, which incidentally was not developed systematically yet. Now I hope this is enough motivation to allow us to, to make us go further and look for symmetries in other areas of operator algebras. And we will look for symmetries of the standard forms. I recall that every W star algebra can be realized as standard phenomenon algebra, and this is a result that goes back to Tomita and Takesaki many dozens of years ago. But I will use the form that was provided by Uffe Hagerup exactly 50 years ago in 1975, who proved that irrespective of whether, the Hilbert space need not be separable, and then a phenomenon algebra, every phenomenon algebra admits a representation like this. On a Hilbert space endowed with an antilinear unitary, in other words, a conjugation, and a self-dual cone. This is in particular a closed convex cone in the Hilbert space, satisfying the following conditions. The conjugation basically gives an antilinear map, antilinear isomorphism or anti-isomorphism from the algebra to its commutant. So the algebra, is unlike the case of L infinity of H, where the algebra is everything and the commutant is very small, just one-dimensional. In the standard picture, the algebra and the commutant have the same size. For elements in the center, this mapping, this isomorphism acts as the adjoint. This cone has the property that it consists of, in some sense, real elements as they are fixed by the conjugation. And we have a kind of quadratic map that maps this cone to itself. These axioms may not be, at least the last axiom may not be obvious, but it is what is needed in order to ensure the uniqueness of the standard form. So every standard form is unique. If we have such a representation, such elements on another space, we will certainly have a unitary operator that intertwines all these structures. If the Hilbert space is separable, these conditions are equivalent to the fact that there exists a cyclic separating vector. But for non-separable spaces, Hagerup expressed everything in this way. He also proved another interesting thing, other interesting properties. Namely, if we consider we have a natural map from the Hilbert space to the predual of the algebra, given by this kind of rank 1 operators. So for every gamma vector in the Hilbert space, we form the corresponding projection. Of course, if this is not norm 1, it is not a projection, but it is essentially a rank 1 projection. For a rank 1 positive operator, and by the trace duality we obtain this mapping. In any case, this is not a linear map because it is quadratic. As you see, it depends, the right-hand side depends quadratically of gamma. And this leads to quite remarkably a homomorphism between the cone in the Hilbert space to the cone in the predual, positive cone in the predual. Why is remarkable? Because as I explained before, the Banach space given by the predual is quite the opposite of a Hilbert space. They are very different Banach spaces, but still we have closed generating cones that are homomorphic. However, as I said, not linearly, they are quadratically in some sense. And with this homomorphism, we obtain a kind of polar decomposition of vectors. Hagerup obtained, namely, every vector in the Hilbert space is obtained, for every vector there exists a positive, in the sense that a vector in the positive cone, and a partial isometry that takes that positive vector to our vector. And the uniqueness, we have a uniqueness if the initial space of the partial isometry is the cyclic projection determined by the vector gamma. So this P, that is why we denote it by P, because we think of it as a positive cone in the Hilbert space. And this is then exactly a kind of similar to the polar decomposition, and except that we don't have here factorization because we have an operator applied to a positive vector. And what I'm going to do next, and it's the main, the first result that we obtained, Anatol Odzijewicz and myself, was to show that all these elements that may seem disparate elements at this point actually fit together in a groupoid. Namely, the statement is like this. If we have a standard form, which was, I recall, a von Neumann algebra on a Hilbert space and the conjugation and the positive cone, then we have a groupoid structure whose space of arrows is the Hilbert space. And the base is the predual of the algebra. The source is the previous map, which is given here. This quadratic map is the source. That is, we think of every vector in the Hilbert space as an arrow starting from this element in the predual. This involution is naturally the inversion map because it is involutive. The target, if we have the source on the inverse, the target will always be the source of the target of an arrow is the source of the inverse arrow. I mean, this is a tautological statement, so we cannot do otherwise, but define the target like this. And more important, I mean, not more importantly, but quite interestingly, is how we use the polar decomposition. Sorry, note. Before that, we have to define the object inclusion map. So we take, in order to take the positive cone in the predual into the Hilbert space, we use the inverse of the homeomorphism that I mentioned before. So you see, we really need this homeomorphism to be actually injective in order to take the inverse. So we have the inclusion of the base of the groupoid into the total space, and the multiplication is defined in terms of the polar decompositions. So if we have two vectors these are vectors in the Hilbert space, and we define this kind of partial multiplication on the Hilbert space using the polar decompositions. And when I say it is a groupoid, it means in particular this multiplication is associative, and we have the other properties that are group-like. So as you see, all the elements, the basic elements of Hagerup's theory of standard forms actually fit together in a groupoid, and that is why we like to call this as a standard groupoid. So every von Neumann algebra has such a groupoid, and it certainly encodes an amount of symmetry. In the exam, what this looks like in the case of commutative von Neumann algebras, then the algebra is L infinity on a measure space. The predual is L1, as you know. The standard representation is exactly the representation by multiplication operators on L2. And in this case, the conjugation is the pointwise conjugation. The source and target are the square root of the modulus. So they go from L1 to the positive cone in from L2 to the positive cone in L1. If we spatialize here this formula, we get this. We need to identify the functions with multiplication operators, but otherwise this is exactly square modulus of gamma. And the object inclusion map is the square root. As I said before, the conditional expectation is in some sense the square is like taking the square of something, and this is the square root because this is the inverse of the, as you see, this is the inverse of the previous one. So these are the mappings that form the groupoid, the standard groupoid in the case of commutative algebras. It is similar, but maybe more interesting in the case of factors of. Yes, and we think of this as a group bundle because the source and target are identical. This reflects the commutativity. In the case of type 1 factors, we have the following picture. So we take the phenomenon algebra of operators on some Hilbert space, but as I said before, the tautological action of this on H0 is not standard because the commutant is very small and the algebra is very big. But the standard representation is the representation by multiplication operators on the Hilbert-Schmidt ideal. So the Hilbert space is the Hilbert-Schmidt ideal. The conjugation is the operation of taking the operator adjoint on Hilbert-Schmidt. The positive cone is the positive cone in the usual operator sense in the Hilbert-Schmidt space. And we have the representation of the algebra by left and right multiplications on Hilbert-Schmidt. And we identify our algebra with the algebra of left multiplication operators. It is well known that its commutant consists of the right multiplication operators, and this is the standard representation. The standard form of this type 1 factor. And how our groupoid looks like, it is the groupoid whose total space or space of arrows is Hilbert-Schmidt, the Hilbert space. The base is the positive cone in the predual. The source and target maps are these. You see they go as written here. And the unit map is this one, is the square root as before, except that now it is the square root in the sense of the functional calculus with for self-adjoint operators. Okay, so far we have this groupoid structure that still already has reflects some internal symmetry of the phenomenon algebra. But for people like you who have experience with Banach-Lie groups and the principal bundle associated to operator algebras, we would like to have even some differentiable structure on our groupoid. So far, I talked only about the algebraic structure. So how we endow this with a smooth structure? In order to do that, we need to describe it differently. To that end, we need to use the support maps, the support of a positive functional, which is the support of functional, as we know, is a orthogonal projection. And the space of arrows will be the set of pairs consisting of partial isometries and positive functionals for which the initial space of the isometry is the support of a state. So basically, the support is the smallest, the largest projection on which the state is still faithful. It's like the support of a measure in the commutative case. With this function, we can define a new groupoid, which will be isomorphic to the standard groupoid. We call it coadjoint because it is in some sense suggested by or resembles the coadjoint action of Lie groups. So in this case, this will be the space of arrows. The base will be again the positive cone in the predual. The inclusion of the cone in this will be like this. We take for a positive functional row, we take its support and itself, and we get a pair here. The source and target maps will be like this. The source of such a pair is rho, is the second argument, and the target is actually the action of the partial isometry on rho. The usual action of partial isometry is on positive functionals. The inversion is given by this formula, which actually it's obtained by solving the equation, if you wish, the equation that gives us the inversion. The product is pretty simple as it corresponds to the multiplication of partial isometries whenever it makes sense. We are allowed to do the product. And I will not pass further before mentioning that once again some properties from this picture were studied before by Esteban Andruchov and Alejandro Varela, who studied established the discontinuity of this map and actually also established some continuity properties along certain orbits. So once again, the groupoids come later, much later, and explain some of the results that were discovered before. And now the fact about this groupoid is that it is easier to make it a Banachly groupoid. And as you know very well, this brief statement says that there exists a Banach manifold structure here and here, such that the structural maps are smooth and so on. But I do not have time to describe the Banach manifold structure. Moreover, for every point in the base, the corresponding orbit is a weakly symplectic Banach manifold. I will not explain what means that fact. I said this only in order to explain why we call this a coadjoint groupoid. And namely, in the case of Lie groups, the Lie group acts on the dual of its Lie algebra, exactly as here, this acts on the predual. And the orbits of the coadjoint action are symplectic, have symplectic structures of a remark due to several people, including Constant, Suryo, Kirillov, and maybe others. So far we have a nice, okay, we call it pretty nice Banachly groupoid. What is important is that it is isomorphic to the standard groupoid. Namely, we use again the expectation map to define a bijection from the Hilbert space of the standard representation to this space of arrows. So for every vector, we take this polar decomposition, and on the first part, we put the partial isometry. On the second, we put the expectation of the positive part of the vector. And the theorem is that the above bijection is actually an isomorphism of groupoid, certainly. But we have here a Banach manifold structure and also on the Hilbert space a Banach manifold structure. So this mapping turns out to be smooth and actually a weak immersion in the sense that its differential at every point is injective. So it is certainly not a diffeomorphism, but it's the same situation that is encountered for foliations. If we think, for instance, of the foliation of the plane by vertical lines, this union of vertical lines is actually a new structure, manifold structure on the plane, for which the identity map is a immersion, a bijective immersion, and not a diffeomorphism. It's the same here. So what we obtain on the Hilbert space, we obtain a kind of foliation by Banach manifolds, which is again a structure to be understood in the future. But it's certainly an example of foliation for in infinite dimensions, a topic, an area that is not very much explored. Okay, so now we also have a smooth structure on our groupoid coming from here, and it remains, as I said, to compare it with this one. Again, and I should mention that related differential geometric aspects of polar decomposition were obtained by Eduardo and Pedro quite recently, since what we are talking about here is basically, in particular, differential geometric properties of a notion of polar decomposition. So again, elements were obtained before, and they resemble pieces of a groupoid. Now, I would like to say that this groupoid has even more structure that I don't have enough time to explain. The orbits are weakly symplectic as this comes from the other groupoid. The groupoid is a kind of disjoint union of transitive groupoids in the sense that they are transitively on the base and which are banally groupoids. Source and target maps behave well with respect to the Poisson bracket. I already explained the Poisson bracket here, and on the Hilbert space we have another Poisson bracket coming from the imaginary part of the scalar product is a symplectic form, and it gives a Poisson bracket. And the graph of the multiplication is an isotropic submanifold here, which is interpreted as saying that the multiplication in some sense is compatible with the two. All these elements, why I mentioned this, because there is a famous notion of symplectic groupoid discovered independently by Karashev and Alan Weinstein. And this, what we are doing here is to show an example of, in some sense, infinite dimensional symplectic groupoid, the first example of that type. So it quite well could motivate development of, or suggest at least to look for other examples of symplectic groupoids in infinite dimensions. However, one problem, because I should maybe stop rather soon. I wish to say that although we have all these structures Poisson, from Poisson manifold are present here, one problem that is not well understood so far is that it is a banachly groupoid, but not with the natural topology on this. So here, this is a closed convex cone in the Banach space in the radial, but we are enriching the topology in order to obtain a manifold structure on the base. Because it is just a pointed convex cone, it cannot be a manifold. So in some sense, we add additional topology in order to get a smooth structure. Still, it would be very interesting to understand what we can do with the initial topology here. And this is a work. This is an ongoing progress with Patrice Auron and Fernand Pelletier to understand in what or to what extent we can talk about the standard groupoid as being differentiable in some, but using the norm topology on this cone. It will certainly not be a Lie groupoid since the base will not be in the classical way because the base is not a manifold. Still, it is a nice closed convex cone, so it does carry some nice structure. And I will finish by mentioning what happens for just by way of motivating maybe further researches, what happens for some basic classes of von Neumann algebras. For instance, for the finite W star algebras, if every isometry is unitary, there are many types of, many examples, the matrix algebras, but also the famous theory of classifying von Neumann algebras of countable discrete groups provide many examples of such algebras. What we can say from the perspective of groupoids, we can say that an algebra is finite if and only if the groupoids are connected. So we have a maybe nice interpretation of finiteness in terms of groupoids. Again, in the opposite case for the purely infinite algebras, or the so-called type 3 algebras, where actually there exists a purely an infinite. I mean, if every projection is infinite, which implies that if the algebra has a separable predual, that actually any two non-zero projections are equivalent. And because of this remark, we can express pure infiniteness by the fact that every non-zero orbit of the standard groupoid has exactly two connected components, namely 0 and the other ones. So even this property can be expressed. And there's another, and I will really finish with this, I promise. Another groupoid incidentally discovered, its uniqueness was proved by Hagerup. As you know, Walenkon proved the uniqueness of injective factors for type 3 lambda with lambda different from 1. And 3.1 was proved later by Hagerup. And I'm talking about that one. And incidentally, also is the one that appears in some areas of physics. Its description or definition is that it is the purely infinite, an algebra is type 3.1 if it is purely infinite, separable, and for every faithful state, its modular operator has a spectrum as large as possible. I'm sorry, what I said, what I tried to say before is that this is type 3.1. What Hagerup proved is that there is only one injective type 3.1 factor. Without injectivity, we have this definition. And we have this characterization of the type 3.1 factor that if a factor has a separable predual, it is type 3.1 if and only if the norm closure of every orbit of the corresponding standard groupoid is a sphere. So the groupoid acts on its base. Its base is the positive cone in the predual. And this action has some orbits. And okay, this is not this is a deep theorem due to Takesaki, the characterization of type 3.1 factors in terms of the unitary orbits. But we can express the unitary orbits as in terms of groupoids or groupoid orbits, and we get this groupoid characterization of type 3.1. Yes. So this is really the last slide. Thank you so much.